So exam 2 is Wednesday, right?
Oh, you could postpone till Friday.
Yeah.
No, we have a quiz on Friday.
That never works. No, that wouldn't make any sense. We have a quiz on Wednesday before Friday's exam.
So Wednesday, 2/21. And the topics are everything up through particle kinetics. And I was asked about number 14 on particle kinetics. I got it right here, thanks. Okay, so it says a 5 kilogram object moves in spherical motion with a radius of 2 meters. So here's the object. It's moving okay, so here's the center of the sphere. Here's the sphere. The object is moving around on the surface of this sphere. The radius of the sphere is 2 meters. Constant angular acceleration vector is 0, 4, -8. At time 0, its angular velocity vector is 5, 0, 0. That's right. Right. And at t equals 5 seconds, the vector from the center of the circle to the object is 0, 0, 2. I guess if we put the coordinate system here, then that's the position vector. So what's the angular velocity vector as a function of time? Velocity vector. Okay, so, and then it just asks us for, a bunch of different stuff at time equals 5 seconds. So first, we want to find the angular velocity vector as a function of time. Well, we know that angular acceleration as a function of time is the time derivative of the angular velocity as a function of time. And so the angular acceleration vector is constant. So we can say d omega dt is equal to alpha. And that means that d omega is alpha dt, and we can integrate both of those. So then omega as a function of time is the integral of 0, 4, -8 dt. And that is 0 plus C1, 4t plus C2, -8t plus C3. And now we can use the boundary condition. That says at time 0, the angular velocity vector is 5, 0, 0. So C1, and then 4 times 0 plus C2, and then negative 8 times 0 plus C3 is equal to 5, 0, 0. So C1 is 5, C2 and C3 are both 0. And so this angular velocity vector is equal to 5, 4t plus 0, negative 8t plus 0. Then for part B, what's the velocity vector of the object when t is equal to 5? The velocity vector is omega cross r. Omega evaluated at t equals 5, just plug in to the function. So it's equal to 5, 20, negative 40. The r vector evaluated at t equals 5. That's what's given at t equals 5 seconds. The vector from the center of the circle, center of the sphere, to the object is 0, 0, 2. So the velocity vector when time is equal to 5 is 5, 20, negative 40, crossed with 0, 0, 2. So that's 40, negative 10, bless you, 0. Any questions yet? And then part C, what's the acceleration vector at time equals 5 seconds? The acceleration is alpha cross r plus omega cross quantity omega cross r. And so alpha is constant. That the whole time is 0, 4, negative 8. The r vector is 0, 0, 2. Omega is 5, 20, negative 40. Cross quantity, 5, 20, negative 40. Cross with the r vector, 0, 0, 2. This one is 8, 0, 0. This one we calculated before, so that's 40, negative 10, 0. And so now all this together is negative 400. Positive 1600. Negative 130. No.
I'm getting negative 392, negative 1600, negative 850.
Well, damn it. Oh, for the whole, yeah. That's right. Wait. Negative 400, positive 1600?
Yeah, positive 16.
And then what's the last one?
Negative 850.
Negative 850. And so then all together, so add up those two parts and you get negative 392, positive 1600, negative 850 meters per second squared. And then the last one, what's the net force? We know that the mass is 5 kilograms. So F net,
That's at 5 seconds.
yeah. F net is equal to the mass times the acceleration of the center of mass. This is a particle, so. And so F net evaluated at 5 seconds is equal to 5 times negative 392, 1600, negative 850, which is 2,000 minus 40, negative 1960. And then 48, 50, 64, 6,400. And then, yeah, come on, jerks.
So it should be also
Not-
negative 1600, not positive 1600.
Is that right?
Unless I did something.
It should be negative, yes. Wait, is that right? Yes, it should be negative.
So that would make it negative 8,000.
Okay, negative 8,000. And what's this one? 4250. Okay, newtons. Because it's y, and y is the weird one.
Why?
Where's the, for which?
Oh, it changed all the way up there, right? Well, no, because it's so it's 5 times 0 minus, it's negative 5 times 0 minus negative 1600, so that is not, that is, yeah, it's negative.
Okay. It's better to have your calculator do that. Like, you tend to be better at knowing what equation to use, and your calculator tends to be better at doing all the, yeah.
So we need to develop an AI.
You need to develop a symbiotic relationship with your calculator. Neither of you is good by yourself.
Yeah, I hate it when I ask you to do a problem for me, and then like 2 lines in, I'm like, that's it.
Oh, you just need to know the direction to go. Yeah,
I totally
right.
could have done that, and I was totally stumped yesterday. I'm like,
Yeah.
I have no idea where to start.
Right, right.
But once you started working, and I'm like, oh my god, I'm an idiot. I should have
Yeah.
figured that out on my own.
Right. The key to it all, I think this is probably the part you like, is just using the fact that alpha is omega dot, And if you see that, then you're like, oh, it's just a simple differential equation, and then you're ready to go.
Yeah, once you started doing that, I was like, oh.
Speaking of that, you should do number 8.
Number 8.
I just, I don't know how to approach it.
Okay.
I'm sure once I figure that out, it'll
Can I use?
So isn't that 1,600? Negative 1,600?
Yes.
Yeah, all these are given.
Oh, yeah, number 8 is the one that I came to on this hour.
Oh, okay.
Figure it out.
Come on. Okay.
Oh, man, because I was an engineer.
You have it there? Oh, you don't?
And that's exactly why I'm not an engineer yet.
I have them all in
now.
I got it. 8. Oh, I was hoping it was that pulley one.
No, it's not the pulley one. It's the one where,
They just give you a function.
yeah, where you have to.
Oh, okay.
You have to build from the position.
Oh, what a pain.
That's what I'm saying.
Okay. So number 8. So we have a 3 kilogram object. That moves according to, well, it moves along the path, follows the path, position is the vector x squared. And I guess, I mean, it needs to be clear about which way, this, what does this path look like?
Parabola.
Yeah, it's a parabola. And so the question needs to be clear about which way it's moving along the parabola. Is it moving in the direction of positive x or negative x?
Depends on that. Well, it starts at 0, theoretically.
It doesn't say anything about what's happening with t, so that's not enough information, really. Like, you might think, like, oh, well, if it doesn't say anything, I'm going to assume positive x. But really, I should have said moving in the direction of increasing x or decreasing x,
If we're not given that, don't we just assume that we don't know the direction in which it's traveling, therefore we just take the derivative of that twice to find out?
No, you need to flip the sign if it's moving in the direction of decreasing x. So you could give an answer for both cases. If it's going this way, the answer is this. If it's going this way, the answer is this. But the path just says. The path just says it's staying on that,
Yeah.
but it doesn't say which way it's going.
Yeah, so therefore we then just take two derivatives of that, so then we know in any case whether it's going in either direction, we have a solution.
No, you need to provide a direction. So I'll point out where that comes in. But because basically we're just using this path to figure out a tangent vector. The velocity is either this way or this way. And if it doesn't tell you, there's nothing you can do. Let's choose this way. That would be in the direction of increasing x. But we'd have to put a negative sign in ourselves if we're told it's going the other direction. So it's following that path. And so a vector tangent to the path
Do we need to know the direction when it's asking what's the net force? Because ultimately, we're looking for the net force acting on the object when x is at 2 meters, and that's a positive value of x. So, do we actually need to know the direction?
Yeah. Okay. So I'll try to clarify as we go with the direction thing. So we know that a vector that's tangent to this path in the direction of increasing x is take the derivative of this path of this parametrized vector function with respect to the parameter. So that's 1, 2x. But that vector is going this way. Okay. If the object was coming along the path back this way, then we're only getting this tangent vector, so because that's the direction of the velocity. We're going to make a unit vector out of that, and then we know the velocity vector follows that. But if the thing's moving back this way, we need to take the negative of that vector, and that would be the vector going this way. But this isn't a unit vector. I'll call this the vector u. And so the magnitude of u is 1 plus 4x squared square root. And so the unit vector is 1 over that square root and then 2x over the square root. And the velocity vector, we're given that the speed is constant 8 meters per second. So the velocity vector is equal to the speed times that unit vector. And so that's 8. I'm going to write this as 1 plus 4x squared to the 1/2. And then this one is 16x times 1 plus 4x squared to the 1/2. Negative, yep. You're right. Okay, and this is v as a function of x. So now the acceleration is dv dx times dx dt, which is dv dx times the x component of velocity. dv dx is negative 4 times 1 plus 4x squared to the negative 3/2 times 8x. And then for the y component, it's 16 times 1 plus 4x squared to the negative 1/2 plus 16x times negative 1/2. I'm just going to make this negative 8x times 1 plus 4x squared to the negative 3/2 times 8x. We want to figure out the net force vector acting on the object when x is 2 meters. So now that I'm done with these derivatives, dv dx evaluated at x equals 2 is, that's still kind of a pain, 16 times 4, 64. So negative 64 over 16, 17, and then for the y component, 16 times, so 16 over square root of 17 minus 16 times 16 divided by 17 to the 3/2. So that's just some ugly number. And then don't forget that, so we're trying to get the acceleration, so don't forget that the acceleration is actually this times the speed. And so the net force,
Dot is the speed.
the dot, dot, dot is the vector up here. The 8 is the speed.
So don't worry about this on the exam.
All I'm doing is copying it.
If you did give us a painful derivative like this, could we plug in the Wolfram on our phone?
I won't. No, I won't put. I won't put anything long in there. I think I've come up with one example where it all comes out nice and clean. So if I make you do something like this, it'll come out pretty nice. There was something with like sines and cosines where it all comes out like a bunch of stuff cancels out. But and then F net.
Wait, we can use Wolfram on an exam?
No.
Okay.
Oh, I thought you said you could use our phones or something like that.
Oh, let's not.
Did you say that?
I said if
You
it.
did say that at one point.
You did, but it was in, I think, a joking manner.
What? No.
Yeah, if you can carry him in. I'll carry in Tom's like this. Why are you here?
Tom's on sabbatical. That'd be hard to find him. You'd have to track him down.
He's up in Tibet. I'm going to go find him. I'll find him by Wednesday.
Okay, let me finish this and then, so 3 times A, so just multiply by another 3, blah, blah, blah. Okay. As far as using Wolfram Alpha on your phone, I don't think we have anything where that's really,
Yeah, if there's not going to be something like
okay, yeah.
I was just worried about making this stupid.
Yeah.
Algebra mistake. And
Yes.
turning it.
Well, if you're showing your thought process and I see that you make, I would never take a point off for.
Oh, you did.
Just
For
like,
me. I
what?
put a negative sign on my first exam, and you docked that.
I'm skeptical, but show it to me again.
Quiz too. I had a negative R.
Well, those quizzes are different because you've already done that problem.
Like half the points gone.
Yeah. I'd be happy to discuss points on old exams if you'd like, but my intention is not to take, what?
What about circuit exams?
My opinion on those doesn't hold a lot of weight. Any other homework questions?
Can we go over 10? It's the one
Yeah.
that you had in the last quiz. Exactly.
Minus a lot of the
Yeah,
Oh,
minus,
yeah.
minus a number. In the quiz you didn't have all A,
Right.
B, C, and D, but
Yeah.
I think I did it right, but I'm skeptical of
Mhm.
the numbers because they're kind of crazy.
Okay, sure. So number 10, there's a carousel with a kid.
So yeah, the one that was on the test. On the quiz.
And it was like one of the two topics for like solution for it, so you kind of went in like, I don't know.
Yeah, there was no solution.
Okay, so this is like the kid from above, you know?
That's way better than my drawing.
Yeah, mine too. Mine's
There's
terrible.
no head.
You guys, he's been giving the same problem for several.
Yeah, that's true. I've had a lot more chances to try to draw these.
He's probably stealing this from some other drawing. I like that he's got a total 90 middle part.
No, those are awesome. And the bulbs.
What if I was really just playing a video on YouTube and just moving my pen around to make it look like I was drawing all this stuff?
That's a pretty good video to predict that I'm going to ask specifically about number 10.
What, no, as far as they know, you're a plant.
Yeah, you are pretty old.
Are you in cahoots? You should see how little he's paying me.
Okay, the carousel has a radius of 2.2 meters.
I thought you forgot the head. Like the fat body.
This very hairy kid without a head. And it spins with a constant angular velocity of 5 radians per second. Okay, this is constant.
Oh, I got this one right here. Or do I need to write this?
What's the contact force applied to the child by the carousel? Oh, I was so lenient on this, but okay, I'll show you the. I basically, if you gave me, I basically was like, calculate the acceleration and then give me any type of force. Any type of force. Gravity, sure.
Wait,
Okay.
we could write that down on our exam?
No, not on the exam, but that's how I graded that on the test. I just remember that now. So,
So should we be proud of that answer then, or no?
well, I'll tell you how.
Yeah, wait a minute. I thought I was so proud of myself.
No,
Now you're like,
you should not be.
You're an engineering student.
Okay, so Z is coming out. What's the contact force applied to the child by the carousel? So that means we need to calculate the acceleration. So the acceleration is alpha cross R plus omega cross quantity omega cross R. And there's no alpha, so that goes away. Omega is positive 5 in the Z direction. R, the way I have it drawn, you could draw it a bunch of different ways, is 0, negative 2.20. So the acceleration is 0.05 cross quantity 0.05 cross 0, negative 2.20. And so that is 1100. And then that is positive 55 in the y direction. Meters per second squared. And it makes sense since we canceled out the tangential acceleration. All we have is centripetal acceleration. Where he is, a centripetal acceleration has to be in the positive y direction, so the direction makes sense. And then the forces, there are, well, you can think of this. Newton's second law says there's a weight force of 0, 0, 20 times 9.81 is 196.2. Plus this contact force. That includes the normal force and the friction force. And that's equal to the mass times the acceleration. So if people just calculated the net force, that's lumping gravity in with it, I gave that full credit. If people did the contact force, I gave that full credit. Just write a force. Any force.
So if we,
That's for Alex Trebek Saturday Night Live skit.
if we write F net equals 20 times 55 and then that equals 1100, on the exam, would that be okay, or do you want us to do the M2L and then all that other stuff?
Is there no
I-
force on that?
The normal force and the friction force are included in this thing. So the only thing, because those are, the contact forces, those lumped together. So the only thing I'm pulling out of this force I'm trying to calculate is the weight.
So you don't really need to specify whether it's a friction or a normal, you can just say, well, it's
Well, I guess for B and C, then it asks for the normal and the friction. So we can do that next. But so,
I mean, I just pretty much did that same thing. I just did a normal force, the weight force, and then I did a friction force. That way.
this is 1100, is that right?
Yeah.
0 plus 0, 0, positive 196.2. And so the contact force is 0, 1100, 196.2. And then you have to separate that up into, for B and C, a normal force and a friction force. The normal force is the one in the positive Z direction, if you just think physically about it. So that's the normal force. That's the friction force.
Does it make sense that you only have friction force in one direction now?
Yes, it would. So friction is only being asked to provide a centripetal acceleration because there's no,
That's the only direction of acceleration.
yeah, there's no angular acceleration. If there was angular acceleration, there'd be a component in x too.
Going tangential to the.
Yes, that's right. And good luck trying to get a friction force of 1,100 newtons with a normal force of 196.2. That kid's going off.
Coefficient of friction.
Oh, yeah, it has to be like
Big number.
I got
wait a
5.6.
minute.
5
Yeah,
point
that's-
something.
That's exactly why I asked the question. I'm like,
Oh, yeah.
That's huge. What is that? Is that like grip tape? That's like super.
Yeah,
It's like-
right.
He's not.
No, he's falling off.
That's
He's going down.
That's what threw me off. Right.
Hands glued to the carousel.
Yeah. Yes.
Can I just ask a quick question about coordinate system?
Yes.
For number 12. You don't have to do the whole problem, but
Yeah.
I just got confused there.
Oh yeah, that was a funky one.
You know, it's just like.
Oh, in the solution?
I don't know if it's probably not wrong. It seemed weird to me.
Anyone have it?
I have it, but I have it written out. I don't.
Okay.
Yeah, it was one where you had the X value going.
12.
I need the one before. The one with the books and the bottom.
Yeah.
Oh, yeah, use this wacky coordinate
You had
system.
the positive X to the left and the positive Z going straight up, so
Yeah.
it has to come out of the page.
Right.
To the right-hand row to work.
Yes, that's correct. So,
Yeah, I kind of just follow what you did.
so first we have to calculate the acceleration, and I'll just set this up and write out what the variables are. So the coordinate system has Z up, X to the left, and that means Y has to be pointing out towards us. And we're looking at the acceleration there. The angular velocity and angular acceleration are that way. So the angular velocity vector, it says the angular speed is 2.5. An angular velocity that's counterclockwise here is in the positive y direction by the right-hand rule. So this is 0, 2.50. And it says it's speeding up at 8.5 radians per second squared. If it's speeding up, then the angular acceleration has to be in the same direction as the angular velocity. So this is 0, 8.5, 0. And the r vector is from the center of the circle to the point. The thing has a radius of 6, so this is 0, 0, negative 6.
mean, does it matter if you chose the X, Y, and Z that way? Could you have done it any other?
You could do it another way and then just convert at the end.
I mean, it's not wrong doing it that way, it's just a different way of thinking.
Right. It's not wrong in the same way that, like, if I ask you this one question and you answer a totally different question, that's not wrong. But you're supposed to answer my question.
With my coordinates system.
Well, it's not very tough. I mean, you put the axes on there, and then you put your right hand on one of them and turn to the other and figure out where your thumb is going, and that's your positive one.
That's right.
Axis that
That's
you're
right.
using.
It was supposed to be just a little exercise in thinking about this coordinate system as a three-dimensional thing and how the things, axes relate to each other and stuff.
I got a lot of trouble with it, but this makes sense out of why.
Okay, yeah.
So,
Yeah, once you figure that out, the hardest part is just making sure you're putting your values in the right spot on the matrix, or in the vector.
Yes.
Well, no, for me, it was like,
Uh-huh.
if we have this coordinate system, is this a standard that we would have to flip to the traditional axes? Or, I mean, for like angles and stuff? Or would we answer, like if we want to go positive 45 degrees, are we going clockwise on this, or are we going counterclockwise?
So it's all determined by the right-hand rule. So if you want to rotate counterclockwise here, since the y-axis is coming out, counterclockwise is positive, you know. If these were flipped, the x was here and the z was here, then that would mean that y had to be into the board, and then a clockwise rotation would be a positive y.
So I'm just wondering is there any instance where we would have to convert that coordinate system into the standard XYZ coming out?
No, not in this class. Although I mentioned once before, I think it's funny that that's not a topic in this class, because if you're actually using dynamics, in any application that I can think of, it's super important to be able to do that, because instant by instant your coordinate systems need to be matched up. But that's just a topic that this course doesn't get to. So, but in D-form we do a lot of that, you know.
Well, I'm in D-form, so.
Yeah. Any other questions? Okay. Well, have a good long weekend and test on Wednesday.
Hope you didn't have a lecture plan today.